Well, how are you doing? Okay, this is going to be a video about the sextant and how it doesn't work on a globe earth. How that is only mathematical and it doesn't work in reality. Okay, this is called, the title of this video is Horizon Line Radius of Equal Angle Debunks the Globe. Okay, so let's get started. I'm not going to spend too much time talking. Okay, this is a depiction of a circle of equal altitude, as you can see here on a globe earth. As you can see, this is on a spherical surface, this circle, and this is the sub point or GP, right, of this star, right. So this is the zenith of the star, right there, right. This is the position of somebody who's taking an angle to the star, and there is between those 2 points, right, between the center and the outside of the circle of equal altitude, there is, here it says 3,000 nautical miles. So this doesn't work on a globe. Like, they have a circle of equal altitude on a curved surface, whereas a circle is a 2D flat depiction. It's always 2D and flat. All radius and diameter are always straight lines. So this is not a radius. As you can see, it's a curved line, so it can't be a radius, and no more than this can be a diameter. So I'm going to move on right from this, and I'm going to show how this is completely not what happens in reality, and how this is totally impossible to work in reality, and how in reality it's always referenced flat, because that is the reality, that the earth is basically across all waters is a flat plane, with the exception of undulations on the water. Okay, so how do you get an angle, right? First of all, you need the vertex and the zenith, right? So you need a perpendicular, so a horizontal and a vertical, right? So this is your 0 degrees out here from your feet. This is your zenith straight above your head, which would be 90 degrees. And all straight lines from your feet, from the ground, right, out in any at any angle to or in any way to any star or whatever, will be the angle to that, right. So here, if you have a star here, it'll be 20 degrees. This one will be from here, it'll be 45 degrees. This one 70 degrees, etc. Right. So you always have to have horizontal and vertical lines, two straight lines, to make an angle. Okay. So that's the very beginning of the use of a sextant, because a sextant is, as they say, a glorified protractor. So you need two straight lines to make the angle to a star or a celestial body, the sun, whatever, before you can do anything else. Okay, so when we want to move on here, I'm going to show how this doesn't work. First of all, on a globe, right? So on a curved surface, here you have this boat making an angle up here, or a line up here to the sun, and this is the sun's GP here. But the problem is that this curved line, they can't make that angle with this curved line. So what they'd have to do is, as this red arrow is depicting, they'd have to, on a globe, what they do is they bring the zenith to the center of their globe, which basically, which is the use of a radius of 3,959 miles, which is what the pre-assumed average radius is of their globe. And they will then treat that globe as a 2D circle. But the problem with that is they're not using the circle on the flat. They're treating as they are on the outside of the circle, and their let's say the top of their mast or the top of their heads is directly away from the center of that circle, as opposed to the center of the circle being at an angle to the top of their heads or the top of the mast here. So as I show here, right, sometimes they try, some of our opposition try and use the very start, like a part of a circle of a part of the surface of their globe up here, to try and make a little angle out of it here, right? That doesn't work, because it's already curving it's curving in all directions, right? On a sphere or on the outside of a circle, it's curving all the time away from whatever point you pick on it. So this doesn't work because when you show here a bigger version, you can see the curve is there, and a bigger version, the curve is there even more. So this doesn't work. You can't get an angle using this curved surface. And the sextant often records that your diameter or your distance from your radius from the GP, which is your ground position of, let's say, the sun or anything, could be thousands of miles. So you can't just use a little angle here and claim that that's good enough, because you don't even have an angle here. Because no matter what you do on the surface of a sphere, the surface is always falling away from your position. So you never have 0 degrees horizontal, because the surface is always falling below it from your zenith. Okay, so I'm going to move on to the next one. Right, this also doesn't work. So pre-assuming flat and then pre-assuming curved doesn't work. Right, I have it up here. The boats are in different positions with a question mark. Right, now I want to come back to how this doesn't work and why this is wrong. Right, this is to do with coordinates. Right, this doesn't work because you can't use flat to get a distance and then pre-assume curved. You can't do the both, and still for it to be correct, it won't be correct, which I was showing a while. It's to do with coordinates and positions. It doesn't work. Now, at this present point, I'm sure there's a lot of people who will be watching this who are from my opposition on the globe side, who will be saying, no, shouting at the screen, saying it can't work, it can't work. Keep listening, keep watching, and I'm going to show you how it's completely impossible, how it doesn't work. Okay. So here you have 3 different boats. Here is the 90 degrees zenith, let's just say, of the sun, right? And here's the GP, the ground position, or geographic position, or I like to call it just ground position, make it easy, ground position of the sun. So this is directly, the sun is directly 90 degrees over this exact point. Here you have 3 different boats. This one's at a 60 degree angle to the sun. This one's at a 45 degree angle to the sun, and this one's at a 30 degree angle to the sun. So the 0 degrees is the horizon is treated as the 0 degrees. This is a horizontal line, right? So they will use the horizon line right here, which would be each one of these boats in this direction would be the horizon line, and they will then use the horizon with their to make the angle, which would be 30, let's say 45 or 50, 60 degrees, and they will then refer to the nautical almanac. When they refer to the nautical almanac, they will then find out, due to the angle they have to the sun, they will then find out what distance, right, the sun is, the sun's GP is in a straight line from them. So it could be, let's say from this boat, it could be 1,500 miles to this point here, and this one here could be 3,000 miles, and this one here could be 5,000 miles, right? So in a straight line distance, due to these angles, referring to the nautical almanac, they can find out what distances each boat can find out what distance it is from the ground position of the sun, right? So that requires, for that to happen, that requires an angle which requires a horizontal line, right, from the boat out to the horizon, and the sun's GP, right, as a 90 degrees. So it's a horizontal and a vertical to create the angle, and the almanac will always tell them, due to their angle, exactly where the sun or star that they're referencing is and how far they are from it, if they have that angle to it. So now we'll move on to the next one. Right. So here is the boat's 90 degrees, right here. Here is, let's say, a 45 degree angle to the sun, right? Here is 0 degrees, right, horizontal, the horizon line. So the boat uses the horizon as a straight line underneath it, right, out towards the underneath of the sun, and it uses the angle then from that point at the water to the sun to find out it's a 45 degree angle, right? And they find out then that that's 2,600 miles or 2,600 miles between their position and the GP, which is the ground position of the sun. Now that means, right, that they can then treat that as a radius. Okay, so double that radius will be a diameter. So if they're 2,600 miles from the GP of the sun as a radius, then their diameter, as I show down here, is 5,200 miles. So a 2,600 mile radius means a 5,200 mile diameter. So that means that a boat at the opposite side of the sun here with the same exact angle will be exactly, let's say, 5,200 miles, give or take a mile or two, from their position. So there's a distance, a flat straight line distance of 5,200 miles between this boat here and, let's just say, another boat over here, right? So that can only work through the use of treating the waters and the earth as flat. That's the only way you can do it, using a 0 degrees horizontal, right? You have to establish 0 degrees horizontal and treat the horizon and the water as that to gain this. And once they do this, this circle, this diameter will then become a circle, okay, after that. But the thing about it is that they have to always treat it as flat to get this. And once they do that, they are always, once you are able to use a sextant and you can use the sextant in this way, you will always be within a mile or two of your destination at most. It's very, very good. Sometimes it's nearly exact, right, by all accounts. So by treating the oceans as flat and the horizon line as 0 degrees, they can be within a mile or two of their destination, and their destination may be maybe several thousand miles away. So if you then make a circle out of this radius and diameter, you then have what they call a circle of equal altitude, but what I'm calling, not that I'm trying to rename it, just for ease of understanding, circle of equal angle, because from the outside of that circle, right, the circumference of that circle, to whatever star or celestial body that is being referenced as with this as its GP, the angle from the outside of that circle to that point will always be exactly the same. So for this example, it's all angles are 50 degrees, all of them. Okay, so this is how it works. It can't work any other way, right? So your circle of equal altitude or your circle of equal angle will always be exact. The radius to the GP from all points of that circle will always be a straight line radius, because you can't create a circle without a straight line radius. Radius and diameter are not ever curved, they're always straight lines. A radius is always a straight line, a diameter is always a straight line. And you need to, and they are the splitting up of a circle. A circle is always 2D, it's not 3D, it's always flat. So, and the radius always goes to the center, from the outside of the circle to the center of the circle. And the diameter then carries on to be double the radius straight across from side to side. From any point on that circle straight across through the middle to the other side will be the diameter. Okay, now this is the problem. This is why the globe completely fails, right? This is the start of where I'm going with this. So where we have, it was like this from The Simpsons or something. The Simpsons. I think it was. This is the globe, a dome over Springfield or whatever. So here you have the line here. This white line is the diameter, right, of the inside of the dome here, and here you have an arc, right? Now I know it didn't match didn't match the dome, but it doesn't matter. It doesn't have to. It doesn't matter. So the inner diameter does not match the inner circle arc, right? So the diameter of any arc, any part of the arc, the diameter of that will always be shorter. So I'll just show here. So here we have a white arc, right, going from point to point on a yellow circle, right? The diameter is less than the arc length. If you see here, this line here, this green line or turquoise, is the referencing the diameter, but this other purple line here is referencing what the arc length would be if it was straightened out. The arc length is greater than the diameter. So the arc length of, let's just say, the diameter within this arc here will always be less in a straight line once they're in distance, or if they're both straight, if the arc is straightened out, it will always be less than the arc, always, right? So this is where the globe fails, right? Because to get a circle of equal altitude, you have to use a 2D circle. You need to treat the horizon, you need to treat the waters as a straight line and the horizon as straight out in front of you. And the only way to get your angle, right? So to get a circle, you have to use a radius. The radius always has to be a straight line, can't be curved, and the diameter is always a straight line. If the radius is straight, then the diameter is straight. So you can't put a circle like this onto a spherical surface and expect the coordinates to match up. They won't, because the arc length of the curve will be more than the diameter from point to point of that curve. So I'm just going to go, wait 1 second now. So here is, see this red line? This is the diameter of this arc, right? The arc is always going to be more than the diameter, always, right? So the diameter of, if we bring it, although it's not a diameter of a circle, if we bring a straight line from here to here, if we treat it like that, this line here will always be less in distance and length than this black line. So the red line is always less than in distance and length than the black line. Okay, I was calling it diameter. It's not really a diameter here, but I'm just calling it that. So for the purpose of, if you can imagine if this red line is a circle of equal altitude and you put it onto the side of a sphere, you can see how it will work, because the arc length will be more, so the coordinates won't match, right? Because the arc length will be more. So if you straighten out that arc here, if you straighten it out, it's going to be bigger than the red line. So if you're getting coordinates and you're using a straight line, which you have to make a circle of equal altitude, then those coordinates can only work on a flat plane. They can never work on a curved surface. You can't put that circle onto a curved surface and claim that it will work. It won't. The coordinates will always be out, because the distance this is covering will only be from maybe this point to this point on this circle, on this arc length. So that's the problem you have. If you put this red line onto that arc, right? But the red line, this won't do it because it'll just match it. But if you put the length of that onto this arc, it won't match the full distance of the arc. So the coordinates won't work. Now, so if we move on to the next one, there's radius, always a straight line. There's a diameter, always a straight line, right? The arc length of this here, right? Half of this, let's say, globe here, right, will always be more in distance than this diameter. Always more in distance than the diameter, because the diameter is based on the radius, and the radius is from the center of the circle or globe to the outside. So the arc will always cover more ground than the diameter. Now, to show you this, right, I'm going to use this, right, the Gleason's map, right. This is a longitude and time calculator. So it's a longitudinal map, right. So this is, let's say, geographic north, and from here all the longitude lines, right, out to the circle on the outside here are all the exact same length. Now, these longitude lines will be always the same distance along those longitude lines on a flat, like in the Gleason's map here, or if you bring in, let's say, this Antarctica here, bring it all in together on the globe, the distance along the longitude lines on flat or curved is always the same. The latitude lines change, but the longitude lines don't change in distance ever. So I'm going to show something here, right? So get out there, right? This calculator, right? So the radius on a globe Earth, right, from the from the center of the globe to the equator line is an average. The equatorial radius of the globe is 3963, I think, and the polar radius is 3950, and there's an average of 3959, right? But the problem with that is, this is the problem, it won't work. That doesn't work on the Gleason's map, right? So if we were to do 69 miles by 90, right, which would be 69 miles a degree from the geographic north center on the Gleason's map to the equator, right? So 69 multiplied by 90 equals 6210. So you would have a radius of 6,210, right, on the Gleason's map, whereas the radius on the globe is 3959, or let's say the equatorial radius is 3963. But I'm going to just minus, right, 3963 equals 2,247 miles. So this is the problem. You can't use a circle of equal latitude, which is used all the time, right? Constantly used, and has to be constantly used by navigators using the sextant. And it always works, right? But you can't then convert that by putting that circle onto a curved globe. It doesn't work, because this Gleason's map shows that there's 2,247 miles of a difference in the radius, right? So the radius from the center here, from geographic north, just using the longitude line to the equator, is 2,247 miles more than the radius from the center of the globe Earth to the outside at the equator. So it doesn't work. The two won't work. So that's why you can't match the two up, because I'm just going to go back to, just 1 second now, right? Just going to take this down, back to here. This is why this doesn't work, because you can't have a circle with a curved radius and a curved diameter. A circle of equal altitude will always be flat. A 2D circle will always be flat. If you bend that circle, right, onto there, then you're changing the angle straight away to the star here. If you straighten out that circle here, if you straighten it out, take it off the curved surface and straighten it out, then the angle changes to the star, right? You can't put that then onto that and expect the coordinates to match. They will never match, because the distances will always be stretched in a different way, flat or curved. So it just doesn't work. And you can't make it work because it's impossible. That's why the circle of equal altitude is always a flat 2D circle, and it always works in reality. It's just that they think by bringing a zenith, right, to the center of their globe, and then taking an angle back out from that by bringing a chord line across, they think that means that it's the same thing. I'm sorry, it's not, because the coordinates don't work. That's only something mathematical you can do afterwards or in between. But if you want it to work, you have to use flat. There is no other way around it. And that's why I said earlier, when I showed here, the boats are in different positions. The boats are in different positions because you can't calculate for flat and then just lay it onto curved, because the coordinates are going to be wrong. Right? The coordinates for these two won't match, and that's the problem, because you're dealing with a completely different aspect. Flat as an aspect and curved as an aspect are two different aspects, so it just doesn't work. So there is no way the Earth can be a globe and sextants can still work. So you want to just go here. So horizon line radius of equal angle debunks the globe. Straight horizontal line radius to the horizon. This is your straight line radius to the horizon. Your star or whatever is going to be up here. That will be your vertical. This will be a horizontal, and you will get your angle to it. And that will be your here will be your radius. Radius is always a straight line. So the radius and horizon proves flat and debunks globe. Thanks for watching.